Uh, okay, hello everyone. Uh, I think I was struggling with whether the video is recording or not. Okay, I think it is recording now. Okay, Mm, I'm sharing the screen here. All right, I was on number 51 in my previous video, so I'm going to continue with that. Quickly, I'll find the derivative here. Okay, so the first derivative will be 18 plus e to the 18 e to the minus x, because the derivative of e to the minus x will be minus e to the minus x, right? By chain rule. So you get that, and that now again is never going to be equal to 0 for any x. You can directly see that. Okay. Why? Because is this, I don't know how it is recorded for you. I'm going to myself on this side. Okay. So it's not going to be 0 for any x because e to the minus x is never 0. So it's never even negative. So 18 plus something never negative is not going to be 0, right? So there is no critical number from that. Oh, sorry. If I was thinking of critical numbers, okay, actually we're not thinking about that here. And also you can say this exists everywhere because that's an exponential function. So actually this is a function which has no critical numbers. So no max, no min. But let us look at the second derivative. Okay. That is what we're interested in right now, the inflection points. And if you want to find the second derivative now the derivative of 18 is 0. It will be minus 18 e to the minus x. Okay, because the derivative of e to the x is uh, e to the minus x is minus e to the minus x, and 18 is the coefficient. Now the point is this 0? No, that's not 0 either for any x, right? So there are no inflection points of that graph, basically. Okay, that's all we need to know. So, and let me just confirm again. Yeah, that's not inflection point. Graph. Why am I forgetting that? I show you graphs, right? Let us look at graphs. Okay, so that was y equals 18x. What was that? Plus 18 or minus 18. I just want to be certain about this. Oh my God. Okay. This is terrible. So they are asking me to sign in again. I'll do that very quickly. Okay. That's the book. It's not your book, by the way. I think I should have told you that in the first video. I forgot. This is some calculus book. Same authors, I guess, but a different book. Where were we? We were in 5.3 exercises. But how come I'm seeing different? What number was I discussing? Oh, these are finding the second derivative below here, below here, below here, here. Okay, number 51 here. All right. 18x minus 18 e to the minus x. That was minus there. So 18 e to the minus x. And as you can see in this graph, you see there is no relative extrema. Okay. Also, sorry, no relative extrema and also no inflection, because it looks like it's concave down everywhere, right? That doesn't even change even if you zoom in. Sometimes you have to be careful, okay? Zoom in sufficiently and you might find a change in concavity, but it doesn't look like that's happening here. Okay. No, it's everywhere. Like it's very small angle, but it's concave down. Focus on that. It's concave down everywhere. Zoom out, zoom out, zoom out, zoom out, zoom out. It's concave down everywhere. Okay. All right. Then let's go to number 53. That might have something to do with the derivatives. Let's find out. Okay. Now the second derivative, we'll jump to second derivative first. Okay. First derivative is 8 over 3, x to the 6 over 3, right? Minus 20 over 3, x to the 5 minus 2 over 3. Oh, 5 over 3, I mean. 8 over 3, x to the 5 over 3, minus 20 over 3, x to the 2 over 3. And second derivative, now notice that those values are still positive exponents. Okay, so that is defined for all values of x. Again, cube root, so there's no problem, by over 3 cube root. And both x's have positive exponents, so that first derivative is also defined for all values of x. Okay. The second derivative, the original function, the domain, let me write like that here, the domain and the domain of f, okay, is minus infinity to infinity. Domain of f prime is also minus infinity to infinity. Let's talk about the domain of the second derivative, okay. That will be, now bring 5 over 3 there, 20, so 40 over 9 x to the 2 over 3 minus 40 over 9 here as well. When you multiply, that's curious case. Okay, I think that is designed like that so you can solve the equation easily. Now it will be x to the minus 1 over 3. Okay, which means now when you take the, if you bring it to the denominator, it will be x to the 1 over 3, and that is not defined at x equal to 0. Okay, so f double prime x does not exist at x equals 0. Okay, so that will be a point we have to, I don't know if you have to consider. I think we'll have to consider that point for for the inflection or not. I don't know. I actually right now I'm confused. Whether the derivative does not exist should be considered or not for inflection. But when you set it equal to 0, we'll see. We'll consider it and we'll check the concavity on both sides. My guess is going to be that it will not be an inflection point because the concavity will not change on the two sides of that point where the second derivative does not exist. Okay. But we will get another candidate when you set it equal to 0. Now, when you set this equal to 0, you get, I'm just going to directly solve it here, okay, without much fuss. The coefficients are 40 over 9. You can cancel them because both are equal coefficients. So you will get basically x to the 2 over 3 equals x to the 1 over minus 1 over 3, when you take it to the other side. And if you cube both sides or bring it to the left side, it becomes x actually. You will get x equals 1. 2 over 3 plus 1 over 3 will be 1, so you get x equals 1. That's your number. How would you solve otherwise? Yeah, that's the only way to solve. So x equals 1. The second derivative is 0 at x equals 1. So let me now erase what I have up here, and I'm going to draw a number line with those 2 points on it. 0 where the derivative, second derivative does not exist. Oh my god, it's so difficult to erase with this. Okay. Change the color. Number line 0 where the derivative does not exist, and 1 where the derivative is 0. Second derivative, I mean. Now that means you are going to take a point on the left side, a point in between, and a point on the right side. And you are going to check the concavity. Okay. Now at -1, if you look at the second derivative, okay, second derivative f double prime at -1. Now I'm going to do another activity on the left side here of evaluating those values, which also will be useful for you. Okay, I'm going to evaluate f double prime at -1. And if you look at the equation, you see x square, right? X to the power 2 over 3, it is squared, so it becomes positive. So that will become 40 over 9. It's 1, so I only need to know whether it's +1 or -1 when you take any exponent. Whereas the second one is cube root, x to the 1. 1 is also odd. So basically the numerator decides whether it will be plus or minus. Okay, so the numerator is odd here. So when you plug in -1, it will be stay as -1. As a result, that will be -40 over 9 times -1. So which will make it then plus, and so you will get 80 over 9. The thing is, it is positive, so it's going to be concave up here. Okay. And when you plug in half, now these things become interesting. Okay. When you plug in half, f double prime of half, that 40 over 9 is a constant factor. Let's take it out. X to the 2/3. Half to the power 2/3 will be 1/4 to the power 1/3. Okay, x equals half. When you do x to the power 2/3, like you are squaring first, x square, cube root of x square. So x square will be 1/4. Then minus x to the minus 1/3, which is 1 over x to the 1/3. So basically reciprocal, and if you do the reciprocal of half, you get 2, right? So I can directly say that is going to be 2 to the power 1/3. Okay. Now I don't need to know, as I said before, I don't need to know the exact value. I only need to know whether it is positive or negative. Now it's because it's 1/4 to the power 1/3 minus 2 to the power 1/3. I can easily see it's going to be negative, so it's concave down here. Okay. Pause the video if you want and think about this, why that value is negative. Or how did I evaluate that expression f double prime x, which is here, by plugging in x equals half. Okay. Then you plug in x equals 2. When you plug in x equals 2, it becomes, I'm going to write that here now on the right side, f double prime of 2. 40 over 9 again is a constant factor. But what you have inside is 2 to the power 2/3, which is 4 to the power 1/3. Okay, 2 square is 4, minus 2 to the power negative 1/3. So 1 over 2, if you take it to the denominator, to the power 1/3. So that is 4 to the power 1/3 minus 1 over 2 to the power 1/3. Now the 4 is dominating, right? So it is concave. Oh, I was wrong. Sorry. So both looks like both 0 and 1 are inflection points because the concavity is changing. Okay, I'm interested to draw. So that means, okay, two things I'm figuring out here. Just like the critical numbers are candidates for maxima and minima, where the first derivative is 0. Similarly, the second derivative also, we have to not just look at where second derivative is 0, but we also have to look at the points where the second derivative does not exist. Consider them as candidates and look at the left and right and then decide whether they are inflection points or not. Okay, and I'm going to graph this and verify the fact. Okay, we are saying 0 and 1 are inflection points. Okay, both 0 and 1 are points of inflection according to our analysis here. Let me recap my analysis before I go to the graph. I found the first derivative, I found the second derivative. I saw that the second derivative has a negative exponent, so it will not be defined at x equal to 0. That is one candidate, for the second derivative, for the inflection point. Then I set it equal to 0 and easily solve that x has to be equal to 1 for that second derivative to be 0. So 1 and 0 are two candidates for inflection. Then I mark the points -1, half, and 2 on the three intervals, divided by 0 and 1 on the number line. And at each interval, I calculated the second derivative just to know whether it is positive or negative. And I discussed how I did that using laws of exponents and things like that. Okay, you can punch that in a calculator. Once you do that, we figured out the concavity is changing from one interval to the other. That means both of them are inflection points. Okay, that was the discussion. Let us graph it. What was the function? X to the 8 third minus 4 times x to the 5 third. I have to erase what I have here and go back to a regular scale. I think I zoomed out too much earlier. Zoomed in too much. I have to go back to normal scale. Okay, this is the normal scale. And let me graph it. Y equals x to the 8 over 3 minus 4 times x to the 5 over 3. Okay, so what were the values? 0 and 1 here and here. Oh, there is something wrong in the conclusion that we drew. At 0, it's correct. This is concave up, you can see clearly on the left side. On the right side, it is concave down, right? So that is an inflection. But what happened at 1? How did we miss that? Or no, that's not 1, not even 1. Where is 1? Oh, that's right. 1 is here. Okay, my God, this is so subtle. No, we are not incorrect. Okay, both are correct. Now imagine, okay, I'm going to point out here. This is where's the 1? Do we never touch at 1? We should. Yeah, 1 comma minus 3, right? That's the point there. And that's an inflection. It's hard to spot. Okay. Actually, not that hard if I was using a little bit more common sense. At 0 here, it is concave down clearly. And at this point, again, like, or even here actually, and if I scroll up, even this region here, it's concave up, right? Clearly, because that's the graph, concave up. Whereas here, at this point here, it's concave down. If it goes from concave down to concave up, somewhere the change must take place, right? And that's taking place here at 1. Okay. Now let us see it more carefully. Actually, if you zoom out too much, it looks like a straight line, difficult to see. Yeah, sometimes that's why, there was a title topic in the college algebra that I teach, the lies that my calculator told me. Okay, so basically, if you use a graphing calculator, you'll not even you will even have less resolution than this. So you may see it basically as a straight line from 0 to 3, but actually the concavity is changing at 1 here. Okay, and we could find that analytically while doing that. Okay, very, very interesting. All right, moving on. What about, okay, 54 is similar. 55, it involves ln, so I'm going to find the derivative and see what's going on. Okay, 55 has ln x square plus 1. Let me scroll it up actually. Okay, so the first derivative, use chain rule. Okay, 1 over x square plus 1 times the derivative of x square plus 1, which is 2x. So 2x over x square plus 1. This time I'm not going to get carried away with the first derivative and get into the mix mean. Okay, let's go to the second derivative. Now the second derivative for this, you will have to use the chain rule. Sorry, quotient rule. You don't do the synthetic division here. Okay, the denominator has larger degree. The synthetic division, what I showed in my first video, works for numerator if it has a higher degree, not when the denominator has. In this case, the only option is to do quotient rule. Okay, and it's not difficult. Denominator times the derivative of numerator is 2 minus numerator 2x minus the derivative of denominator is 2x divided by x square plus 1 whole squared. Denominator squared. Okay, simplified, 2x square plus 2 minus 4x square. So it's clearly 2 minus 2x square over x square plus 1 whole squared. Now you see what is happening here. Numerator is 2 times 1 minus x square, which is 1 plus x, 1 minus x over x square plus 1 squared. Okay, now that is the second derivative. When you look at the second derivative, a couple of things. Now, from the previous problem, we know that the candidates for inflection are where the second derivative does not exist and where the second derivative is 0, right? And what we find here, the denominator, that's never 0. So the second derivative does not exist, will not happen, by the way. Okay. Not only that, one more thing I want to tell you, even though there is ln here, by the way, okay, going back to the original function also, the domain is still minus infinity to infinity. Think about that. Now, if you thought about it, you would have seen that it's because we have x square plus 1, right? So no matter what x you give, see, the domain is not about what is input for ln. Okay, the domain is about what values of x can you give. Now the input for ln has to be positive, we know, but then because it is x square plus 1, it is always going to be positive no matter what x you give. It will be more than 1 actually. So the range actually in this case, will be greater than ln1 or greater than 0. So range will be non-negative from 0 onwards. Okay, the values of outputs will be 0 or more, but the input can be anything. And this is an even function. For plus x and minus x, when you square, you get the same thing. So you are going to get, symmetric with respect to y-axis. Okay, but basically the entire domain. So domain-wise, no issues. By the time then you might think, okay, then there might be points that we have to consider as critical numbers because they are not in the they are in the domain. That's not going to happen because the denominator in the first derivative and the second derivative is x square plus 1, and that is not going to be 0 again. Okay, so the only type of candidates for inflection points or critical numbers would be where the numerator is 0. So the only critical number is x equal to 0 actually, because the derivative is 2x over x square plus 1. And the only candidates of inflection points are x equals 1 and minus 1 based on the numerator there. Okay. And let's do it. Let's mark minus 1 and 1 there. Okay. And we can take other points in between. Minus 2, let's say take 0, and let's take 2. And let's evaluate the second derivative at those points. Now, if you go to minus 2, 1 plus x will be 1 plus x will be negative at x equals minus 2. 1 minus x will be positive because x is minus 2. Minus minus will make it plus. So plus and minus, so it will be negative concave down. At 0, 1 plus 0, 1 minus 0, positive. So it will be concave up. And at 2, 1 plus 2 will be positive, 1 minus 2 will be negative. So concave down. So again, it looks like, sorry, not there. I should have drawn that concave down this side. Okay. So it again looks like both minus 1 and 1 are inflection points. Okay. Concavity changes at both those points where the second derivative is 0. Why not look at the graph? Okay. That's the conclusion. I'm going to erase this. And y equals ln parenthesis x square plus 1. Okay, yes. Again, not very easy to see, but you can figure out that on the left side it's concave down, but by the time you are closer to 0, it is concave up, right? That is changing at minus 1 from concave down to concave up. And again, it is concave up for a while, but in the long run, it is concave down, right? So it looks like that up to down change took place at x equals 1. Hence minus 1 and 1 are inflection points. Okay. Very well. What are some other things we are discussing here? Okay, there are absolute value functions and things like that I'll not get into too much of that right now. Okay. What is it saying? Give approximate value where x is min max. Intervals where it is decreasing, increasing. Inflection points. Okay. So this exercise below this, from 75 onwards, this is asking you to do the same exercise, but now you restrict to that interval. Okay. So whether it is critical points or the second derivative, once you find the values where the second derivative is 0 or does not exist, first derivative is 0 or does not exist, before you make any conclusion about that point, you have to check whether it is in the interval given here. Okay. Now, both x and y, I think it appears are given. How do I get rid of this? Okay. minus 5 by 5, minus 5 comma 5 by minus 5 comma 15. What do they mean? That means that is x and y given, I guess. Okay, so it's basically the rectangle. We are looking at a rectangular box and the graph, the part of the graph which is within that box. So you have to check both x and y values, and only if it is within that box, then you consider it. Otherwise, you discard it. That's the, I think, moral of the story. Okay. I don't know. I have few minutes left. I want to demonstrate at least one of them. Hopefully, we'll have something which is not in the box, to illustrate my point. Okay. Let me take the first problem and give a try. If you find the first derivative, that is 3x squared minus 12x plus 7. Okay. 3x squared minus 12x plus 7. I'm not sure if it has any simple solutions. If I set it equal to 0, I get x equals 12 plus minus under root 144 minus 28 times 3 will be 84 divided by 2 times 3, that is 6. Okay, that's 12 plus minus under root 60 over 6. Are they greater than 5 or less than minus 5? That's what we have to see. I don't think they are, as I see them here, because that's going to be 2 plus minus, you divide by 6, both of them. Okay. Under root 60 is what? 15 times 4. So 2 root 15 divided by 6. Okay, so that will be under root 15 divided by 3. Under root 15 is close to 4. 4 divided by 3 is 1 point something. So it's not basically going to be more than 5 or less than minus 5. But we have to see the output also. Oh, that was f prime of x. I'm sorry. I have to find f double prime of x. My bad, my bad. What I wrote here is f double prime. Anyway, now both the points are the x values are between minus 5 and 5. Okay, that's fine. But what about the y values? Let me read the question again. Is there anything? Sometimes the derivative of function is known, but not the function. We will see more later. Each function is different. Oh, in the window below, I see. So that is the x and y limit given. And this question was meant to be done in a graphing calculator. I get that. Okay. I did this analytical part here. So these 2 points are, the x values are definitely in that window of the x values given there, but not sure about the y values. Okay, that only the graph will tell you. Okay. All right, I think I'll leave at that. There's no point in discussing further. On the number line, you can mark those points. Okay. That is why it is a graphing calculator. Analytically, it's not simple. It's tedious. Okay. I think, folks, I'm going to stop recording at this point. I did made 3 videos. Hopefully, it helped you. And I will discuss, of course, more problems, more ideas. Not this topic, I guess. I think we have to move on from this topic. Not this morning. Okay, I've got some other work to do now. Later on, if possible, I might make a video where I do the sketching of the graphs. Okay, which I think is a topic we have discussed, but I have not discussed in these videos. If I get time, I'll do sketching of a graph using the first derivative, second derivative, and all the information. And I think that definitely that would be the last video on this topic that I need to make. Okay, I will let you know if I post that. Otherwise, I'll see you in class. Bye.